I remember that there's a formula to find the range, like an easier formula to find the range or to find u.
True. But the problem with this formula is it only works when you're on horizontal ground, which is not always the case. So I recommend to students not to bother with this formula because it's only going to work in limited cases. It's better that you learn the method for all cases, you know. But you can use it if the situation arose. That's perfectly fine.
Yeah, because at school the teacher told us you're not allowed.
Yeah, this I feel is the common opinion of most physics teachers, and I would agree, but I wouldn't say not to use it. I'm not going to forbid it, but I'd recommend that you don't use it.
No, he was like, I'd let you know, but you're not allowed to.
Yes. It's because as a student you don't understand it's for your own good. It's better if you don't know of it or use it. You might be thinking, stinking teachers trying to make my life harder, but really, it's really not like that, I promise you. Okay, so I have one new-ish student and one new student. Very good, okay. So I need to give you a book and I need to get you a book then, so I'll bring that for class tomorrow. So we're in the middle of doing mechanics. Do you know this word, mechanics? Yeah, Newton's laws and all that. So right now we're about, let's see how far in. We're about, there's 25 lessons and we're on lesson 16. So you see that you've missed a bit. But I record all the lessons. So the lessons that you missed, they're recorded and they're on YouTube. So anyways, we'll talk at some point maybe about what you might need to do to catch up, okay? Bruce, I think you'll be able to catch up, okay? Yeah, you're a smart guy, you can catch up. Yeah.
Simple guy.
Simple guy, are you sure? Oh, okay, if you say so. Alright, work! So if you can write this down, this is where we're continuing from. You got that? Come on, Bruce, where's your notebook?
Yeah.
Yeah, let's make notes.
Maybe in other notes.
No, make new notes. Yeah? Thank you. Okay, so work. Right, so we have this picture here and we can see work is being done. But, with the help of the picture, just think about what things are needed for work to be done. So what do you need in the picture to be able to say work is being done? So what does this have? What things are going on in the picture? Do you know what I mean? Like, why can we say he's doing work? There's a force, and there's a distance, good. And these are kind of the main things that you need. Because he's using a force to move something, a distance, we say there's work being done. So there's a force, the man is shoveling, the force is making something move, so the sand's being moved. And in this picture also notice that the force and the movement is in the same direction. So, if he moves it to the left, the force is also to the left. Usually we have force and movement in the same direction, usually. And usually the force is over an area, in this case the shovel. So there's an area as well. Now that's not as important. So for the new people, you don't need to write all of this down, just whatever notes you feel you need to take down from the slide. There's nothing too important on this slide, I just want you thinking about work. So precisely what is the definition of work? So I'm sure somebody remembers from high school, if they've done it before, what the definition of work is. Anyone remember? Don't be shy, I'm sure somebody remembers. Bruce, do you know what the formula for work is? What?
For what?
For work.
With a distance.
Yeah?
They will make work.
Yeah, and what's force and distance? How do you put them together? Do you add them?
No. Multiply.
Multiply them, yeah. So, work done is defined as force acting on a body, and if the direction and the displacement is the same, you just multiply the displacement by the force. So, in other words, it's a formula. It's simply work is force by displacement by distance. W is work, F is force, and S is displacement. So you'll need to write this formula down. Work is force by distance. And of course, the distance and the force, they must be in the same direction. I have a message from the other students. They say they miss you. Do you want me to tell them anything? What will I tell them? Okay.
You got it.
I get it. Yeah. Bruce said he's happy he doesn't see you anymore.
You said I'm gone. I heard about this.
Yes. Yes. Yeah. Will I do that to them? I say this is from Bruce. Okay. Okay. I won't say.
Very handsome.
Okay.
Thank you, help.
No, I'm not so kind. Okay, did you write this down? Yes? I did know your name, but I forgot already. The principal told me. What's your name again?
Jessica.
Yes, now I remember. Dubai or Saudi? I forget which country. Oman. So none of those two. Okay, you just really need the formula. I mean, you can write the whole thing down if you want, but the formula is what's key here.
If they ask for definition, can you just write product of process?
Yes, you can in the exam. Don't feel bad. Okay, what's the units? Yeah, but I didn't tell you that yet. That is true, but if you were to use the yes, what is it? Ooh, close. Newton meter, yeah. The unit is the joule, which in fact is a Newton meter. We say 1 joule of work is performed when 1 Newton displaces an object by 1 meter. It's the same as 1 Newton meter. Okay, so you do need this definition, please. New student, you have studied some physics before, right? In high school, yeah? To what level? Like what level would it be similar to? Would it be like A levels or more or less? Less or more? Which, like how would you compare it? Like what you studied, would you say the same, easier or harder than A levels? A little easier than, yeah, okay. But you've done, all this is familiar. Did you study in English or Arabic?
Arabic.
Okay. But you can translate. It looks familiar. You studied in English or Arabic, the physics? English, okay. So all the words are familiar to you then. Yeah. Okay. Continue? Yeah. Continue? Yes? Okay. So we'll do this one together. This is, you don't have to write this down. This is just to get us thinking. Where and what is doing the work in each of these examples? That is, what has work done to it? So the first one, a mother lifting her baby up from the ground. Who is doing the work? The mother. And what's the work being done to? The baby. And what's the direction of the force Upwards. Okay. A woman pushing a large box across the ground. Who's doing the work? The woman, and it's being done to the box, and the direction is horizontal. Good. A man kicking a football, so who's doing the work? The man being done to the football, and the direction probably horizontal. Now it's getting harder. A child hitting the wall. Who's doing the work? Maybe. I don't know. You would feel you're burning calories if you're hitting the wall. So some work is being done. Yeah. Who's doing the work here?
No water.
Oh well, if you really think deeply about it, I think there is some work being done. Who's doing the work? The child is doing the work. Child. Yeah, it doesn't have to be a child. A person hits a wall. So the person's doing the work. To what? The wall. But what exactly is the force and the work being done? Like, what is the force and what is the distance?
Distance is the distance between charge and point.
It is not actually.
Why?
Because the distance is only the distance for the force. Yeah, what do you think? You're going to say something. Well, if you really, really think about it, the displacement's not zero.
Is there any reaction?
There is a reaction, yes.
But the wall is not moving.
True, but what is moving?
No.
The hand is moving. So if you think about it, if this is the wall and this is the child's hand, when the child hits the wall, there's definitely a force, and the distance is the distance his hand compresses. Yeah, it's like a car crashing into a wall. There's a strong force over a very small distance. The hand compressing, the muscle and the bone compressing. This is the distance and the force. Yeah, this is why his hand would hurt, because the work being done by the hand, the force and the distance on the hand. So it's not the distance from the wall, the distance the hand compresses while the force is being applied against the wall. Yeah. You don't
Why
seem...
does the wall change?
I suppose if you hit it hard enough, the wall would also move a small distance. Yeah. Let's say it's a concrete wall. The wall doesn't change its shape. Just the hand changes the shape, not the wall then. Yeah? You don't look happy with this. You're doubting me. Go on, what's your question? No? It's okay?
No problem.
Okay. A father carrying his child. Who's doing the work? Well, the father. Being done to the child. But what exactly is the force and the distance here? So if the father's walking with the child on his shoulders, what is the force and the distance? Good, yes, true, but what's the distance then? So you're right, the force is the father supporting the child's weight, which is equal to, the gravity force. That's true, but what's the distance though? If I draw a picture here, it might help a little bit. So here's the father, and here is the child. You get the idea. And he's walking that way. So you're right, the father is providing an upward force. He's pushing up to keep the child up, and this would equal mg for the child. But what's the distance? Yeah, what would you say? The center to where or what? Okay, the difference between the centres is the distance. Not bad, you're actually not too far away. It's not this great though. It's not as big as this actually, but you are thinking along the right lines. So I was hoping to trick somebody and to say this distance, but of course this is wrong. Why? Why is it not that distance? The distance he walks.
No single way.
Because the force is the distance.
Yeah, exactly, yeah. It's not the same way as the force. So the distance must be here.
The power.
Yeah. Is it this height? Well, oh, the ground to the centre. Good, but no. It's actually just a, yeah. Yes, yeah, or the muscle, yeah. You see, the distance is quite small because when the child is on the father, all the father is really doing is pushing up a little bit. The distance is, Bruce said, is only really the distance of maybe his muscles. You know, because as the father is walking, all he's doing is keeping the boy up. He's not lifting the boy up every time he walks. It's just keeping the boy on his shoulders, which is just really a bit like with the wall, just a little bit of muscle distance, that's all. Or maybe muscles in the back. Anyway, the reason I have these examples is it's not always clear what the force and the distance is. I just wanted you to be careful with that and to think about it. But you don't need to write this down, this is just to get you thinking. And the last one was interesting because, remember, the force must be the same direction as the displacement, and that's important. So if the force and the direction weren't the same, so let's say, for example, I don't know, here's something here, and there's a force this way, but the block moves that way, let's call that distance s, then the work here would not be F multiplied by S. What would you have to do? Yeah, you would have to resolve. Yeah, so this is theta, what's this one here? F cos theta, very good. Fs cos theta would be it here. So just make note of this formula, please. This is just if there's an angle. Oh, who's calling me? I don't want to answer. Do I want to answer? No, I don't. Stop ringing. I do private maths lessons. People call me every day looking for help. You wrote this down? Got this? Yep. Okay, continue. Yep. So, we've done that. Okay, let's have a look at a question. A woman pushes a 100 kilogram box along a smooth surface by a horizontal force. The block starts at rest and reaches 1 meter per second over 5 seconds. Okay, so let's just draw that here. Here's a block. This is 100 kg. She pushes it with a force and it moves a distance of, I don't know, it starts at rest and it gets up to 1 meter per second, and it took 5 seconds for this to happen, so it ends up here. Okay, part A, I know you can do this. I hope you can do this. What is the acceleration of the block? Okay, so I'll let you try this first. Just try part A first. What's the acceleration? Do you remember your formulas from high school? Your UVATS formulas? You remember? Did you use VI and VF or U and V? Ah, good. VI and VF, wasn't it? Yes.
No, that's me.
Yes. You know them, V squared equals U squared plus 2AS? Ah, okay. Let me just write them down for you then, to help remind you. V squared equals U squared plus 2AS was one of them. S equals UT plus a half AT squared. V equals U plus AT, and S equals U plus V over 2T. Looks familiar?
Yeah.
You don't sound certain. Okay, well, you'll have to use one of these formulas for part A. We have an answer? Should be small. 0.2 sounds about right. Which formula did you use? Which one? Oh, just A equals V minus U over T. Which is actually like which one here? It's like this one. So, V equals U plus AT. So, A is 0.2 meters per second squared. Okay, part B. What have we got here? What's the distance? Okay, so get the S now, please. Got an S? Sounds about right. Which formula is best for S here? Yeah, or even this one here actually, right? Yeah. S equals U plus V over T over 2 times T. So that's 2.5 meters. Okay, C. What was the force? Okay, so what formula gives us the force? F equals ma, good. So that's 100 times 0.2, which is 20 newtons. D. How much work was done by the woman? So what's the formula for work? Force by distance, which will be 20 by 5, which is 100 joules. Of course. 2.5. 50 joules. And lastly, if instead she applies the force at a little angle of 10 degrees, what is the work done now? Yeah, it just multiplied by cos 10, isn't it? 50 cos 10. What's that? 49.2 joules? Yeah.
Should we multiply that by 2.5?
That 50 is already like this part. If you want, it's really 20 times 2.5 times cos 10. That's Fs cos theta. Do you know what I mean? Or am I confusing you?
Oh, okay.
Continue? Yes? Okay. You have that? Alright. There's another element at play here though. So tell me, why does standing on one foot feel more difficult than on two? Yeah, well the gravity force is the same. You haven't changed your weight. But what's the reason that it would hurt more on one than two? The area is different. So not only is the force important, also the area. So this ballerina here has the same force but a very small area. I think I told you about this last time, didn't I? What did I say? If you want nightmares, you should Google image ballerina's toes. Yes. Not pleasant pictures. Not pleasant. Did anyone Google it? No.
Pretty bad.
Did you Google it?
Google and warn me.
Yeah. Yeah, warning. Just, it's not pretty. Anyways, we can see it. The other element at play here is the area. Come on. Well, you can kind of, once this resumes, you can kind of see what I'm getting at. What do you think I might be leading into when we're talking about force and we're talking about area? Pressure, yeah. There we go. So pressure means how much something is pushing on something else. Exactly the definition of pressure is, well, I'm sure somebody knows this. Pressure is, force per area. Yeah, P is pressure, F is force, and A is area. Now, what are the units according to this formula for pressure? What would be the units from this formula? That's it, Newton per meter squared. Or Pascal. So the units are pascals, and we say 1 Pascal is felt when 1 Newton of force pushes at right angles on 1 meter squared. This is a Pascal. It's the same as 1 Newton per meter squared. Can you see?
No, I can see.
No, you can't see. Everybody can see? Okay. Not yet? Sure. I'm not going anywhere, don't worry. Are we all just waiting for... No, you're still writing over here. Now you finished? Continue. Yes. Good. Okay. So, here's another example. It's exactly the same as the last example, except I want to know what's the pressure in her hands, and I give you the area of her hands. So, pressure is force over area. I'd like you to calculate the pressure. You already know the force. The force is 20 newtons. Wasn't it 20 newtons? Yeah, 20 newtons. But there's one small problem. What's the problem with the area here? Yeah, you'll have to convert it into meters squared. Okay, so try and get the pressure here. You got an answer? Pascals? Could be. So let me see if I got my calculator. No, I don't. Okay? We get answers? We got an answer, yeah? So you have an answer, do you have an answer? What did you get? That's the same as you, pascals, or 2 kilopascals, yeah? Did you get an answer? Yeah, okay, so let's have a look. You get an answer? Did you get the same? Are you sure? Okay. Where's my calculator? Come on. Yeah, you have to change the unit. So just to be clear, 100 centimeters squared is actually 100 centi squared meter squared, which is 100 times 0.01 squared meter squared. Which is 100 times 0.0001 meter squared. What's that? 0.01 meter squared. Yes? So the pressure is the force over the area. So that's 20 over 0.01. Right? No, you all made a mistake. Before I type in the right answer, does anyone tell me the mistake that was made by the class? Read the last, read the question again. Yeah. So the area is twice this, 200 centimeters squared. Yeah, so it's 2 times 0.01. So 1 kilopascal. Gotchas. One kilopascal. Yeah. To this? Yeah. Two hands. Yep. You're writing that down. You got it? Okay. Alright, so you have the questions there. It's about 5 minutes just to practice some of them, and then we'll go on to the next lesson. Can you share that? Oh, actually, there's 3 of you and one of the books. Oh, you have it already. Yeah. Work! No, before that. Next. No, too far. No, go back. Stop! Work.